Now the importance of knowing what geometry we have tells us the bond angles, which is great, but it's also going to give us a better picture of the 3D shape of these things. The problem is when we look at the 3D shape on paper, it's really hard to draw that 3D shape as nice as these pictures show. Okay, so we need a way to draw these 3D shapes on our own. So if we look at the linear shape here, we can just draw two straight lines 180 degrees from each other. The linear shape is pretty easy to draw. If I go to the trigonal planar, I draw three straight lines, keep them equidistant from each other to get my trigonal planar. That's how I draw this on the 2D paper. Bent, well, I just basically take my linear, the way I drew my linear, and put a little bend to that, put an angle to it. Okay, keep in mind, above that A though, I could have lone pairs. I don't show the lone pairs here, but I usually like to put those in. Okay. With my tetrahedral, the thing you need to recognize is the black wedge represents things coming out of the plane of the paper. The dashed line represents things going behind the plane of the paper. Okay, any straight lines that you see are assumed to be in the plane of the paper. So if you're drawing this on paper, straight lines are on that plane, wedges are coming out, dashed lines are going behind it. Okay. With the tetrahedral, I don't know why they drew it this way. It looks goofy to me because I usually draw it like this. So I have the x's with the straight lines are in the plane of my paper that I'm drawing on. The wedge is coming out of that paper. The dashed line is going behind that paper. Okay, that gives me a 3D shape to look at. When I go to the trigonal pyramidal, well, all I'm doing to get a trigonal pyramidal is I'm taking one of those bonds away and replacing them with a lone pair. So I just use the same tetrahedral shape, except one of those becomes a lone pair. Now you don't need to draw the straight line to the lone pair. You can just put the lone pair on top of the A. I put it in there just so it makes it easier to see what got replaced from the tetrahedral shape. Okay, if I look at trigonal bipyramidal, you can see that I've got three of the x's and the A are all in the same plane of the paper. One x is coming out of the paper, one x is going behind it. That gives me my 3D shape. Seesaw, I've got an x, an A, and an x, all linear that are in the same plane of the paper. I've got an x coming out, an x going back, and technically there should be a lone pair on the A on the left-hand side. All right, when I go to octahedral, I've got an XAX that's linear in the same plane of the paper. I've got two x's coming out away from it. I've got two x's going behind it. And then I end up with square planar as my last one here. With square planar, technically all of those atoms are in the same plane, which is why they drew it this way. The problem is if you want to give it a little bit more shape, it's hard to put in the lone pairs when you're doing that, because technically then the lone pairs are on the front side of the paper and then the lone pair is behind the A, behind the paper. Okay, so usually with square planar, I draw it like this. So I basically take those linear x's from the octahedral and replace them with lone pairs. Okay, so those are ways that I'm going to draw these 3D shapes on 2D paper. And you need to be able to draw these structures. So not only do you need to be able to predict them, you need to be able to draw them out. Okay, so let's go through some examples of these. So what we're going to do is we're going to predict the electron domain geometry, molecular geometry. We're going to draw an appropriate 3D structure, and then we're going to predict the bond angles. Okay, so let's look at SEN 1-. So the first thing you need to do is draw an appropriate Lewis structure. Once you get that, then you need to predict its electron domain. So its electron domain is going to be linear. Its molecular geometry is going to be linear. So when we draw the 3D structure, we get something that looks like this. Now it's going to look pretty much like our Lewis structure looked like, our 2D Lewis structure. Since it's linear, it's all going to look pretty much the same. Now if I want to predict bond angles, if I look at that bond angle between the sulfur-carbon bond and the carbon-nitrogen triple bond, be 180 degrees. Okay, and don't forget, just a reminder, around that carbon we only have two areas of electrons. Why? Because whether it's a single, double, or triple bond, as long as it's between the two same atoms, counts as one area of electrons. So that triple bond there only counts as one area of electrons to determine our electron domain. All right, let's look at another example. SF4. So I'd want to draw the Lewis structure for SF4. Then I'd want to predict its electron domain. So when you draw the Lewis structure for SF4, you're going to end up with an electron domain that's trigonal bipyramidal. You're going to end up with a molecular geometry that's going to be seesaw. So when we draw the 3D shape for that, we end up with this shape. That's a seesaw shape. With the seesaw shape, my two fluorines there, I've got a bond angle that's going to ideally initially be 90 degrees. But in this case, it's going to be less than 90 degrees. Why? Because I have that lone pair on the left-hand side of the sulfur that's pushing all of those other electrons away, all those other bonds away from it. Those sulfur-fluorine bonds get closer together, so that bond angle is going to be less than 90 degrees. These sulfur-fluorine bonds are going to be less than 90 degrees. Right? And these sulfur-fluorine bonds, because they're pushed away from that lone pair, are going to get less than 180 degrees. All right, let's look at XEF4. So, you draw the Lewis structure out first. From that Lewis structure, you can predict an electron domain. Electron domain is going to be octahedral. The molecular geometry then is going to be square planar. So when we draw that out, we get a 3D structure that looks like this. So I've got two fluorines coming out, two fluorines going back, and then two lone pairs. Okay, if I look at the bond angles on this, bond angles between those xenon fluoride bonds are going to be 90 degrees. Those are going to be 90 degrees. Those are going to be 90 degrees. Now wait, why aren't they less than or greater than 90 degrees? Because I have lone pairs. But keep in mind, in square planar, I have a lone pair on the bottom that's forcing all those bonds up and away from that lone pair on the bottom, but then I've got a lone pair on the top that's counteracting that and pushing them back into place. So there's no change in bond angles. Okay, so those are just some examples of predicting these geometries, drawing their appropriate structures, predicting bond angles. First thing you need to do, though, is you need to be able to draw those Lewis structures, those 2D Lewis structures. If you can't do those, you can't predict the electron domain, you can't pick the molecular geometry. Now, we've been looking at single-centered molecules so far, but we can treat this on different centers around the same molecule. So, if I take this particular model here, this carbon with 3 hydrogens bonded to another carbon, which is double bonded to an oxygen, and also single bonded to an OH group. Okay, so a CH3COOH is how we describe it. I could draw a 2D representation initially of a 2D Lewis structure would look something like this. Well, then what do? Well, I want to predict the geometries around each individual central atom. So, if I start with that carbon on the left, it's got the 3 hydrogens attached to it. Well, it's got 4 areas of electrons around it, right? It's got 4 bonds, which means it would be a tetrahedral shape. Okay, what about the next carbon? Well, it's got 3 areas around it, so it'd be trigonal planar. All right, what about that C double bond O oxygen? Well, that oxygen has 2 lone pairs and then an area of bonding electrons, so that's 3 areas of electrons. So technically, it's going to be trigonal planar. However, because 2 of those are lone pairs, we typically call that linear. But when we arrange those lone pairs of electrons, we try to put them at an angle to make it look more trigonal planar. What about the oxygen that's got the H on it? Well, that's going to be bent. It's got 4 areas of electrons. 2 of them are lone pairs. So if I start with 4 areas, that's tetrahedral electron domain. 2 of them are lone pairs. That gives me a bent molecular geometry. Okay, so we draw it as bent. All right, so put it all together. When we draw it out, we'd get something that looks somewhat like this. Okay, and you can see the CH3 is the only thing really that changed that had those wedges and the dashed lines added to it. So now we can take that and we can predict bond angles around those, since we know their molecular geometries. So we'd expect those to be 109.5 degrees, the carbon hydrogens there. We'd expect the carbon-carbon and the C double bond O to be a little bit greater than 120 degrees. Why? Well, because that double bond takes up more space, has more repulsive forces, so the C bond C and the C bond O are going to get closer and closer together because you're getting pushed away from that C double bond O. So those are going to be less than 120 degrees from each other. And then because we're dealing with a bent coming from the tetrahedral, we got those 2 lone pairs. We'd expect that bent bond angle to be less than 109.5 degrees. Okay, so that's going to take us to the end of these geometries. So keep in mind, you need to be able to distinguish between electron domain geometries and the molecular geometries. You need to know the names of all those. You need to be able to draw the 3D structures for all of those. Right? All of that comes back to, though, initially getting the correct Lewis structure in the first place. Okay? Once you know those geometries, you can predict bond angles. All right, but that's going to be it for these molecular geometries.